All set? Well, our last but certainly not least speaker of the day is Jeroen Zuiddam. Jeroen did his research, his PhD research here at CWI, defended his thesis at the University of Amsterdam. He received a degree cum laude. After that, I think Jeroen went to a postdoc to the IAS in Princeton. And now Jeroen is at the University of Amsterdam. Jeroen found surprising relations between the connections between Shannon capacity and matrix multiplication through the semi-ring theorem of Strassen. And I think that is, again, part of your lecture. Please go ahead, Jeroen.
Definitely. Thanks a lot, Lex. It's nice that you're here because you're the one who introduced Shannon capacity to me in like 2014 or something in advanced...
but the main fault is there, eh?
That's true, yeah. Yeah, discrete math course. So, all right, let's get started. So this talk starts with a guy named Strassen. He's here in the picture. He published a seminal paper in '69 called Gaussian elimination is not optimal. And this paper sent a clear message to the scientific community, to the community of algorithm designers in particular, and complexity theorists. And this message is that natural, obvious, and century-old methods for solving important computational problems may be far from the fastest. And well, he didn't state this message like a sentence like this. What he did is the following. He looked at these very central problems, right? Matrix multiplication, inverting n by n matrices, solving a system of n linear equations in n unknowns, and computing the determinant of an n by n matrix. These problems are all algorithmically equivalent, like complexity-wise, they're equivalent to each other. And what he did is that Strassen proved that the obvious cubic algorithm for these problems is far from optimal. And he did that by designing a new one, which takes only n to the power 2.8 operations, right? So if you have a large matrix, then of course you save a lot of time solving any of these equivalent problems. Now, yeah, the possibility of obtaining even faster algorithms made everyone very excited, and people started looking into this problem. And here I've drawn a graph of the exponent. Right, the interesting thing is the exponent of n in the complexity bound for this problem. And this started at 3, right? Cubic algorithm got to 2.8 in '69 by Strassen. After that, we have a curve here. It's not a smooth curve at all, of course. It's an approximation here. That came down all the way to 2.37. Dion was already mentioning it. And people are still looking at this. So the quest to understand this matrix multiplication exponent, which is often called omega, is still raging on. So that's that. But Strassen didn't stop there. He kept his whole life. He kept thinking about this problem. And decades later, in '86, from '86 to '91, Strassen developed his theory of asymptotic spectra. So it's some abstract theory, which was motivated by trying to understand the complexity of matrix multiplication. Okay. But it was not. You cannot only apply it to this problem. It turns out. It turns out to be a much more general theory, and this has led to like a broad framework that suits other problems and settings, and that's what we're going to talk about. So let me say on a high level what's this theory about. So central in this theory of asymptotic spectra is the following question: what is the cost of a task if we have to perform it many times? Yeah, so you have a task, you want to perform it many times, and you wonder what's the amortized cost, right? Can you gain economies of scale when you have to do many copies of this task? And this arises in numerous parts of mathematics, physics, economics, computer science. Some examples are matrix multiplication. Turns out to be of this form. It turns out to have this recursive structure that you can interpret in this way. Circuit complexity is an area where I applied these ideas with Robert Robert. Direct sum problems, that's a very general class of problems that Avi also likes a lot. And the last one here on my slide is Shannon capacity. Shannon capacity is going to be the problem I want to talk about in the rest of the talk. But yeah, before I go there, so this is a very interesting, I find this a very interesting area, of course, that's why I'm talking about it. And Avi and I wrote a survey on this topic, which you can find on my website. This is like a 120-page plus survey, so it's, yeah, we really try to capture this theory there and explain things in a nice way. Here's a picture from when we were thinking about these things at the Institute. You see that we are very happy. That's probably why the paper became so long. Actually, I think we were laughing because the photographer was hiding somewhere. It was the Institute photographer. She was hiding and trying to take a secret picture of us. And then we were discussing like how to distribute the royalties. I think that's what I think that's what happened. So yeah, here's the picture. Okay. So, like I said, I want to talk about Shannon capacity. I will need to define it. Then I'm going to talk, then I'm going to introduce the asymptotic spectrum of graphs. 3 is a duality theorem, which is based on this asymptotic spectrum of graphs. So, and then the final part is going to be consequences and new directions. Okay. Yeah, well, let's get to it. So Shannon capacity, let me just say some words first before diving into it, something more mathematical. Shannon capacity measures the amount of information that can be transmitted over a communication channel when there's noise. Understanding this parameter, the Shannon capacity, has been an open problem in information theory since 56. So Shannon introduced this in 1956. Yeah, so that's in words what the Shannon capacity is about, how it's motivated. It translates to a graph theoretical problem, and that's the language we're going to use, the language of graphs. And in this translation, what happens is that you have this communication channel, right? It has some noise. This noise pattern translates to a graph. Okay, so we're going to talk about graphs. They correspond to the channel. Then a good, efficient protocol that's resistant to the noise on this channel that corresponds to the graph is going to correspond to a so-called independent set in the graph, which I will define. And then we have the idea of, we want to not send a single symbol over this channel. We want to keep sending more and more messages over this channel, right? So we're going to repeat this. That's what I talked about earlier when you have a task that you want to do many times, right? This repeating, that's going to correspond to something called the strong product of graphs, which I will also define. So these are graphs. We have 3 graphs, right? We have a 5-cycle star graph, and this is what I call empty graph on 4 vertices, right? There are no edges. And in a graph, we can define independent sets. Independent set is a subset of the vertices that doesn't induce any edges. So in the 5-cycle, we can pick these 2 vertices. They don't induce any edges, right? They're not connected at all. In the star, I can pick these 3 guys. They also are not like pairwise. They're not connected. So they also form independent sets. Yeah. Of course, in the last one, this is just for vertices. So I can pick all the vertices to be my independent set, right? They're all not connected. So that's an independent set. And what we're interested in is large independent sets. And this we call the independence number. So the size of the largest independent set in a graph is the so-called independence number, and we denote it by alpha. So here we have the 5-cycle. Its independence number is 2. This is really the best you can do. Yeah? Independent set of size 2. In the star graph, the independence number is 3. This is the optimal independent set. And in these empty graphs, it's always the number of vertices, right? So alpha of E, I call it E4 here for empty graph. Independence number is 4. Yeah? Very good. Now, so we have a couple of notions defined that I mentioned earlier. But we want to do this repetition thing, right? So we need this strong product. I'm going to define it in a way that I hope people can understand. So the strong product is a product on graphs. Yeah, you have two graphs, G and H. And we define the strong product with this box times. The vertex set becomes the Cartesian product of the vertex set. Yeah. And for the edges, what I find easy is to define it using the adjacency matrix. So to a graph, of course, we associate the adjacency matrix, right, labeled by the vertices. The columns and rows are labeled by the vertices. We put 1s on the edges, and we put also 1s on the main diagonal. And then to know what the edges are of a strong product, you just look at the adjacency matrix. I define the adjacency matrix of this product to be the tensor product of the adjacency matrices of G and H. Yeah? So if you know how the tensor product works of a matrix, then you know how this is defined now. So that's the strong product. So what we're interested in here is how does the independence number behave under this strong product? And what's easy, well, I won't show it, but what's easy to prove is that the independence number is supermultiplicative. So alpha of G times H is at least alpha of G times alpha of H. If you have an independent set here and here, you can kind of multiply them. You can take their tensor product. And it can also be strict. That's why it gets interesting. So for the 5 cycle, the independence number was 2. But turns out that's really interesting that if you take the square of the 5 cycle, the independence number actually becomes 5. So it's not 4, it's not multiplying. It actually goes up. And what we're interested in the Shannon capacity problem is how much does it go up? Like what's the rate of growth? And so here's the definition of the Shannon capacity. So we have a graph G, and then we have this capital theta, that's the Shannon capacity. This is defined as the supremum over n of the independence number of the nth power of the graph, normalized with the nth root. Yeah? So it's measuring a rate of growth. You can replace this supremum by a limit. That doesn't change the definition. And it turns out that this is a parameter that's very hard to compute. Okay? It's extremely hard to compute this already for very small graphs. So for the 5 cycle, it was determined by Lovász that the Shannon capacity is square root of 5. So this construction is optimal of an independent set in powers of C5. But then if you go to C7, so the 7th cycle, just a little bit larger cycle, right? It's already not known what the Shannon capacity is. And the best bound, so the upper bound is also from Lovász's techniques. And the best lower bound is by Schrijver and Polak, Sven Polak, who's also here in the room. But you see, yeah, they get quite kind of close, but it's not known. So that's a big goal, to kind of try to understand what kind of new methods are necessary to compute this Shannon capacity of small graphs. Let's start, I want to start a bit simpler. How can we upper bound the independence number? So I want to talk a little bit about this. Yeah? And then we move from there. So there are I want to kind of talk about 2 techniques. They both work with matrices. And the first one works with matrix rank, and the second one works with eigenvalues. Okay? So here's one. This one uses matrix rank. So the goal is to upper bound the independence number. I'm given a graph, 5 cycle in this case. And to this graph, we associate a matrix where it's labeled by the vertices. And what we do is we put 1s on the main diagonal. And we put 0s on all the non-edges. Yeah? So wherever the graph is a non-edge, we put a 0 in this matrix. And the rest we leave open. The rest you can put whatever you like. I put stars, so you can fill them in however you like. Then what can you do with this matrix? Well, what happens is that if you have an independent set in your graph, and you look at the corresponding submatrix of this matrix, any such matrix, whatever the stars are, then you get an identity submatrix of the size, the same size as the size of the independent set. Well, this means that the rank of this whole matrix, right, must be at least the size of this identity submatrix. So in conclusion, independence number is at most the rank of any such matrix that we take here. And we can optimize over the stars, right? Try to get good upper bounds on alpha. And it turns out actually that this also upper bounds the Shannon capacity. Okay, I won't go into that, but it also upper bounds the Shannon capacity. I hope it's clear how that this works, right? Finding this identity submatrix and that it's upper bounded by the rank. So this is kind of, this is maybe the simplest way, I would say, to upper bound. One of the simplest ways to upper bound independence number using a matrix. Now comes another method, which is a bit more clever, and sometimes also much more powerful. And this is using the largest eigenvalue, and is due to Lovász. It's called the Lovász theta function. I will not describe it very formally, but we're going to go over a similar kind of game. So again, we have a graph. We associate to it this matrix, but now I still put ones in the main diagonal, but instead of zeros on the non-edges, I'll put ones on the non-edges. This is a very simple change. Very natural change, actually. Zeros and ones, kind of natural numbers to use in this kind of, right? If you don't know what your field is. In this case, actually, the field is going to be reals. We're going to work over the real numbers. The stars are open. You can put whatever. Has to be symmetric, doesn't matter. Okay, so we play the same game. Every independent set, in this case, gives an all-one submatrix, right? So what is the next step? What do I do now? So matrix rank is what we used before. I'm now going to use the largest eigenvalue, right? The largest eigenvalue of an all-ones matrix is just the size of that matrix. And it's a kind of well-known fact that then that this lower bounds the largest eigenvalue of the full matrix, right? So in other words, the independence number is at most the largest eigenvalue of any such matrix. Okay, so matrix rank is now replaced by largest eigenvalue. And what's very surprising, and that requires some thought, is that much more work, is that this also upper bounds the Shannon capacity again. Yeah? So there are these two techniques, and they upper bound the Shannon capacity. You can ask, how good are they? And are they good enough to reach the Shannon capacity? Right? Are these methods sufficient? You can think of it as some sort of proof, like a proof model. Like these are the methods you're allowed to use. Are they strong enough? And to talk about this, I want to introduce this thing called the asymptotic spectrum of graphs. So we're going to zoom out and make a more abstract definition, which kind of encapsulate both the Lovász theta function and this Hamer's bound, and then we can say something more about it. So what we're going to do is, we define this asymptotic spectrum of graphs. What it does in words is it will model graphs as points in real space. Graphs are, of course, combinatorial objects, but we're going to somehow map them into real space, high-dimensional real space. It goes as follows. So this asymptotic spectrum of graphs is defined as a set, which I call X, I call it X because I don't know what it actually will be. It's a set of functions, maps F, from all graphs to the real numbers. And they have four very special properties. These are also properties that the Lovász theta function has. So the first is that this function F has to be additive under the disjoint union of graphs. If you have two graphs, you take the disjoint union. We want this function to be additive on this. They have to be multiplicative under the strong product, which we defined, right? We want these functions to be monotone under cohomomorphism. I'm not going to say much about this, but this is a cohomorphism is a map from vertices to vertices that maps non-edges to non-edges. And whenever you have this between two graphs, we want the value of the function to be non-decreasing. Okay. Finally, we want our functions to be normalized to 1 on a single vertex, when you have a graph with a single vertex. Yeah? So it's completely not clear what's in this set. maybe to relate back to this first thing, so if you want to map this to real space, what I meant is you just apply every function to your graph. So you get like an infinite sequence of real numbers. So that's how you can map a graph into real space. But so what happens is that there's some examples of elements of X that we do know, and the Lovász theta function is one of them. The Hamer's bound is one of them if you make it fractional. So you have to somehow allow rational numbers in a certain sense, instead of rank, right, which is always a natural number. And there's the fractional Klikover number. These are some examples, and we do know some more, but we don't know all of them. Okay, so that's a definition of a very complicated set. Now, what can we do with this? So I want to define a duality theorem. So recall that the Shannon capacity is a maximization, right? This is supremum. And the Lovász theta function, or the Hamer's bound, they give upper bounds on the Shannon capacity, right? I claimed this before. We saw it for the independence number, but I claimed it for the Shannon capacity. And what's kind of easy to see, that's kind of the starting point, is that every element in the spectrum, every such function, also gives an upper bound on the Shannon capacity. And now I ask this question again: Are these upper bounds powerful enough to reach the Shannon capacity? Okay, now it's a more formal kind of statement. And the answer is yes. That's the duality theorem. So the Shannon capacity, this duality theorem, which my theorem says that the Shannon capacity, which is normally a supremum, a maximization problem, can also be written as a minimization problem. So for every G, we minimize over all elements in the spectrum, the asymptotic spectrum, and we evaluate that G. So this Shannon capacity is now a minimization problem. So we're going from the other direction. Yeah, so maximization, minimization. I think, yeah, there's one important question that needs to be asked now. If you see this theorem, I wonder if someone has a worry about this, seeing this duality. Like before even thinking about how the proof would go. Like there's an important question you should ask.
Is the minimum attained?
That's one thing, but I wrote minimum, so yes. But there's another important question you should ask, like about the theorem when you see it before looking into the proof, maybe. Yes. Who asked this? Yeah. Is theta and x? Or in other words, is this theorem actually non-trivial? Yeah, because I show you this theorem, but maybe it's completely trivial. So the question is the duality theorem non-trivial? So what could happen in this duality theorem is that the Shannon capacity is itself in X. Then we're not doing much. Right? And this was actually a conjecture of Shannon, that the Shannon capacity would be in X. But it turns out to be not the case. So there are two theorems here, by Hamer's and by Allon. Hamer's proved that the Shannon capacity is not multiplicative, and Allon proved that it's not additive. And so either of them show that the Shannon capacity is not in this set. Okay, so we're really dealing with some non-trivial duality over here. Yeah. So the other question then is, how do you prove this kind of thing, right? I won't say much about this. We have this whole survey, so you can go there. So I will just say some words. So there's a slightly more general duality theorem that deals with co-homomorphisms between powers of graphs. And this, yeah, if you look at this, there's certain ideas that go into this proof. So it's really something that takes place in real geometry. It's some sort of positive Stellensatz, if you've ever heard of this. In particular, what you can do is use a theorem called the Cadisson-Dubois representation theorem to prove these kinds of dualities. You can also think of this duality as an extension of linear programming. So that's also something I like to. That's also a way I like to think about it. I won't say much more about the proof. I want to talk about some consequences and then some new directions. So here's the consequence of the duality theorem. And so the way I say it's, yeah, in words I call it additivity if and only if multiplicativity. Holtzman mentioned this to me. So this is a statement for any graphs, G and H. The following are equivalent. There's three statements. The first is the Shannon capacity is additive on your graphs if you take the disjoint union. The second is that the Shannon capacity is multiplicative. And the third is that there is a function in your spectrum such that it attains the Shannon capacity for your G and also for your H. Okay? These three are all equivalent, and I'm going to give a proof of one direction, just quickly. I want to do 1, 2, 3. 1, 2 implies 3. So let's see how this goes. So what do? I know that by the duality theorem I can take a function f that attains the Shannon capacity on the disjoint union, right? Then what do we see? We have assumed 1. So I know the Shannon capacity is additive on these two graphs. It's attained by f, and f is additive. So we get this. Then what we always have in any situation is that Shannon capacity is at most f. Yeah? These f's give upper bounds. I told you this. So if we combine this, we have this sum is equal to this sum, and the components are upper bounded by these components. So then they must be individually equal. Yeah? So you have Shannon capacities f on G and H. Yeah, that's how you go from 1 to 3. 1 implies 3, sorry. Going back from 3 to 1 is quite easy. I won't do it. But so the point is, it's easy to go from here to here and back. And of course, you can do the same for multiplication. There's not much of a difference between addition and multiplication in these kinds of proofs where I don't do much. Right? Yeah. So this is a theorem I like, and you can, of course, apply this theorem to these counterexamples of Hamers and Allon, right? Because it shows that they are equivalent to each other. If you have one, you can actually find the other. If you have an example where it's not multiplicative, then you also know that for the same graphs, it's not additive, the Shannon capacity, right? There's another nice thing you can do with this, which I like. There are other ways of proving this. What I'm showing now is not new, but there's a cute argument here. The Shannon capacity, remember, it's the supremum of the independence number of powers of a graph, right? So you're going over all natural numbers there, or a limit, you could say. And interesting question is the Shannon capacity attained at a finite power? Or do you really need to go all the way to infinity? And this additivity, even only if multiplicativity, allows you to very quickly do kind of arguments about this. So here's an example of this. So I take C5 times a single vertex, which is just C5. It's just isomorphic to C5. And that means that the Shannon capacity is clearly multiplicative on these two graphs. The Shannon capacity of C5 times a single vertex is clearly equal to the Shannon capacity of just C5. So it's multiplicative, the Shannon capacity, and hence it's additive, right? That's what this theorem says. So that means that the Shannon capacity of C5 disjoint union and single vertex must be square root of 5 plus 1. And this number you cannot write in the form an integer to the power 1 over an integer. So that means that the Shannon capacity of this graph, this guy, cannot be attained at a finite power. You really have to go all the way to infinity. Okay? It's just a small example application. You can do this more generally. Avi and I looked at this. You can replace multiplication and addition by arbitrary polynomials in this nice way, where you have that for every polynomial, we have that the Shannon capacity commutes with the polynomial, if and only if there exists a polynomial for which is the case. The polynomial has to depend on all the variables. If and only if we have this same statement as before for the spectrum. I like this. And we can make this quantitative as well. So you can bound like non-additivity in terms of non-multiplicativity, for example. All right. That was some of these applications. So I want to talk a little bit about new directions. Just one slide and then some problems. So I just listed a couple that I'm thinking about. So in the paper with Avi, in the survey, a big part of it is about the idea of looking at the topological structure of the asymptotic spectrum. Yeah, so you can think of the asymptotic spectrum as a topological space, actually. And what's very interesting is to understand, for example, in general, also for other situations, it doesn't have to be Shannon capacity. Is this spectrum disconnected, or is it connected, or Is it star convex or is it convex? Right? This is going from weak to strong. And stronger topological structure leads to new algorithmic methods. So you do want to prove as much structure as possible on this spectrum. So that's one interesting thing. Another topic I'm thinking about, which relates to Lovász's talk, is new notion of graph limits. This is also something that Sven, Polak, and Lex have thought about. And so the way this starts is that you can use the spectrum, the asymptotic spectrum, to define a distance on graphs. So you have two graphs, and what you can do is you can go over all these functions and just look at their difference and take the supremum. Right? And this turns out to be quite interesting and not so easy to understand. And with David and with Piotr, who are PhD students here at the University of Amsterdam, we've been really trying to come up with all kinds of methods. We have some powerful methods now to construct Cauchy sequences, right? In this setting. And like one question is, of course, are all Cauchy sequences do they converge to a graph, for example? Turns out that it's not complete. So we can actually have some Cauchy sequences that do not converge to a graph. And we don't really know what the limit objects should be, or like whether it's at all related to other notions of graph limits. We don't know. We're thinking about this. Haddad-Niemi properties is another interesting topic. I'm thinking about it with a master's student. There's a nice set of lecture notes actually by Yuval Wickerson, Avi's son, which I really recommend on this topic of Haddad-Niemi conjecture. And finally, with Visu, I've been thinking about these direct sum problems, where you want to know how a certain parameter behaves if you or it's like when you have solve many copies of a problem. You want to know, can you gain economies of scale? And we've done this in other areas, in particular for tensors. All right, let me finish with some problems. This is really a random kind of collection of problems. I have many more, but one thing that that's really interesting, and of course way too hard to solve because it would tell us what the Shannon capacities of every graph is. What are the elements of the asymptotic spectrum of graphs, right? Or what's the structure of this, or anything you can come up with. We really don't know much. What other problems in math, CS, and physics have asymptotic spectrum duality? I have found applications, but there must be many more. And another question that maybe doesn't really fit in, but it also does, is that I'm really interested in is is there a way to extend the Lovász theta function to hypergraphs? Right, it's something that I've thought about it with people, and that would be really interesting. Right, it's not clear how this eigenvalue notion will generalize. All right, so final message here. I think, studying the computational complexity of natural problems. I think, that's what this theory and all this survey of us showed, is that studying the computational complexity of natural problems may both require and generate deep and sophisticated mathematics. So I invite everyone to look at our survey, which is on my website, and I stop here.
Thank you very much, Jeroen. What are the questions? I see a few hands. Make your choice.
Hey, I just wanted Philip to come here to bring me the microphone. That's a joke. The thing is that you said that the Shannon capacity is the amount of information that can be transmitted through a channel, right?
Yeah.
And then you give a definition in terms of a graph.
Yeah.
First, how do you relate these two things? And second, I was wondering if in particular you have a quantum channel, CPTP map.
Yeah.
How do you pass from this to the graph to compute the Shannon capacity? Thanks.
Yeah, so for the first question, the way it works is that you have a channel, and you're allowed to send a certain set of symbols into it, and then on the other end, symbols come out. What the channel does is it sometimes confuses symbols. So it might confuse A and B. So it might turn an A into a B and B into an A. So there's a certain noise pattern, and we specify the noise pattern, so the possible confusions you can have. And this is how you get the graph. So the graph is the vertices are the input symbols, and then you connect them if they can be confused in the channel, if they might lead to the same output at the end of the channel. And then, yeah, you have to think a little bit about what does it mean to have a good protocol. I want to communicate with zero error. I don't want to allow any error. And then what you need to do, you see this very quickly, is that you need to come up with an independent set in this confusability graph. You really want to use only symbols that can never be confused at all. That's how it goes. Taking the power, you have to also look at and see that it corresponds to sending multiple symbols through the same channel. That's the first question. And the second one is more complicated. I can't. Yeah, it's a very interesting question about how do you make a quantum. I think there are also several ways of doing this. So yeah, but that's a very good question. Yeah.
Okay, the next question, please. Here, yeah, it's this side. Go on, please.
Yeah, so here you say that the elements of the asymptotic spectrum are not at all clear, but you sort of do know that there are enough of them to take this minimum. So is there a way to construct them, or do you just know that there are enough?
Yeah, we don't really have a good way of constructing them. But somehow hidden in the proof is that the spectrum is non-empty. So in a sense, the proof does give a construction, which corresponds to the fractional Klikover number. I think that's what it comes down to, which is one of these points. But other than that, yeah, at first you only know it's non-empty, and then you really need to somehow come up with more.
Can I ask a related question on your previous slide?
Yeah.
Because there you say supremum f over x, but x is compact. So you can take maximum.
Probably
the same as you earlier took minimum over, isn't it?
I think so.
So, but that makes the whole theory depending on the axiom of choice.
Yeah, but that's in any case, well.
Because x is compact because of the axiom of choice.
I think also in the duality theorem, I don't know. I use the axiom of choice to prove it, yeah.
Yeah, if you say infimum, you don't have trouble, I think.
Yeah, I see. Yeah, it appears in the proof, the axiom of choice. Yeah.
Yeah, because you cannot construct the f. I mean, it's an infinite set of values. Okay, sorry.
Yeah.
Next question.
Yeah. It's good to worry about.
Yeah, there is the question. Yeah.
Yeah. So adding to that, you showed us 3 examples of points in the asymptotic spectrum of graphs. Do we know any others?
Yeah. Yeah, it turns out there's a way to interpolate between them. Not an easy kind of interpolation. You cannot take a geometric or arithmetic average. That doesn't work because it won't satisfy the properties. But you can actually, we do know it's connected. You can actually make paths between points. Yeah, so you get whole family. And in fact, even without that, we already knew there were more. You can, you can take the fractional Hamersbound for every field.
Willem is here, eh? Willem Hamers.
Really?
Yeah, he exists.
Excellent. Cool. You can do this over every field. This matrix. The Lovász theta function you can only do over the reals. But the Hamersbound you can do over every field, and it turns out that these also give independent functions, which is not trivial. That's Boeg and Koch's result. Yeah.
And then another quick question, if I may, or just So
go ahead. Yeah.
Quick question. So the Hedind-Némi properties you mentioned. So are these related to Hedind-Némi's conjecture?
That's exactly what I meant.
Yeah. So it's related to different graph products. Maybe.
That's right.
Yeah.
That's right.
Yeah.
A graph product which I think of as taking a minimum of 2 graphs. So we have an addition and a multiplication, right? Then you can add an extra product, which is called categorical product. But I think of it as like a minimum of 2 graphs. And then the question is, for Hedind-Némi, you want to know whether the minimum of the chromatic numbers is the chromatic number of the minimum. You can ask these questions about points in the asymptotic spectrum.
Okay, Daniel?
Yeah, I was just curious, do we have any sense to what to what limit these problems are actually decidable?
No, I don't know.
So
that's another.
But even for just say Shannon capacity, not for like tensor ranks and these things.
Yeah, for Shannon capacity, yeah, you can ask this about all of these amortized problems, and maybe there's some general theory about it. We don't have it yet. For Shannon capacity, I also don't know it, decidability. Yeah, it's a very good question.
Peter has a question.
It would be nice if the duality theorem has some
Thank you.
implications.
If I understand correctly, these asymptotic spectra are functions from the graphs into
Reals.
the reals. Now, that means they are living in a highly dimensional space. And if you are asking whether this set is convex, are you then referring to the elementary linear interpolation structure of this higher dimensional space, or is there something abstract going on?
No, for example, yeah, or convex or low convex. What I like to do, you can make it finite dimensional. There's a way of making it finite dimensional. The way to do that is that you focus on a finite set of graphs and look at, and you're interested in the Semmering generated by these graphs. And then it's enough to just evaluate these generators at the elements in the spectrum. So if you have Q generators, you end up in a Q-dimensional real space.
Yes, but the problem is that if you require that the function is both additive and multiplicative, how can you attain that if you do linear
It's amazing,
interpolation?
but it happens. So there are examples where it happens, and no, it's not easy to prove. Exactly what you say. You want to remain additive and multiplicative.
But that's the Semmering theorem you use. Eh? I mean, you didn't mention it, but somewhere in the proof, I mean, it's hardly non-trivial actually. Especially because the Semmering theorem of Strassen, eh?
Yeah, but he's asking, can it ever happen that it's like a convex set?
Oh, yeah, yeah.
And this happens in the matrix multiplication setting. This does actually happen in certain cases, like the tensor setting. There are examples where it actually convex.
More questions? Doesn't? So at the back there.
Oh no,
sorry. Oh, I didn't see it. Sorry. Go ahead.
Well, I was just wondering, is there some example of some mathematical object, not a graph, but maybe something else, where we also have this like a product and direct sum, and where we know fully what is the asymptotic spectrum?
Yeah. And the easiest example, there's a canonical example of Semmerings, which is you take a topological space. Matrices you can also do. So you would take matrices. The Semmering of matrices under direct sum and tensor product. It turns out that the spectrum is a single point. It's just matrix rank.
Yeah.
Right, but okay, and do you know, is there also some object where, like where you know, like basically could you like bound, upper bound and lower bound the, like the, I don't know, Shannon capacity, like basically could you have another family of objects where you can compute this asymptotic spectrum, or you know some elements in the spectrum that would bound the corresponding things for graphs?
Yeah, you're asking, can you relate the asymptotic spectrum of graphs to another asymptotic spectrum for other objects? Yeah, I like that question. Because that's kind of what the Hammersbound, in a sense, does. You have matrices and graphs, and kind of the Hammersbound is kind of relating these two Semmerings. But for example, for the theta function, I don't know how to do this. If there's a nice Semmering that somehow, it's a very natural question.
A last question of a backbencher, I should say, the last row, please.
Hi, thank you for your presentation. The spectra I'm looking at, they are continuous. It's a dense thing what I'm seeing there, no?
Yeah, so, well, these are pictures. So, but it could be that it's really disconnected, just a finite number of points. That's also possible, depending on your setting. Yeah.
The spectra I know are from, for example, Toeplitz operators, either continuous or discrete. They form a line or a set of dots. There's a German that did a lot on bounded symbols, Albrecht Butcher, and it has to do with mathematical physics fields like photonics, or finite arrays, infinite arrays, periodic structures, Floquet modes. What does your, to which field does your theory relate?
I have no idea.
We can expand further discussion maybe after till the reception.
Sounds good.
We
Thanks.
stop it. Sorry, but.